In this video, we're going to cover utility maximization, which is what you get when you put indifference curves together with budget constraints. So to me, this is the most central, the most important, the most primary topic or assumption in economics. It's really what, to me, everything else revolves around. And so this assumption is that people are rational, which in this context means that they maximize their utility or their happiness, subject to their budget constraint. So I tried to kind of take this out of economics speak and into English that most people would understand. And the best that I could do is that no one has an infinite amount of everything. We know that. That's just kind of how life is. So we use what we have to make ourselves as happy as possible. So that as happy as possible is that we maximize our utility. And the use what we have is that we are subject to a budget constraint, so we can't have everything. So that hopefully that makes a little bit more sense than we maximize utility subject to a budget constraint, because to me when I first learned that always was kind of just gibberish. So really what we're saying is that we take all the resources that we have, and in our finite amount of time we make ourselves as happy as possible. So now let's get down to kind of the mechanics of it, the graphs, the formulas, and all of that. That's a little bit more not down to earth, but a little bit more practical, I guess. So let's say that John has $40 to spend on apples and oranges. Apples cost $2 and oranges cost $2. So how many apples will he buy and how many oranges? So we are assuming that John is rational and that he wants to maximize his utility. So we've been given his budget constraint that he has $40 and apples are $2 and oranges are $2. So let's just I'll do this in purple to kind of color coordinate everything. So budget constraint 1 is that $40 has to be equal to, and we have $2 times the quantity of apples plus $2 times the quantity of oranges. And I've gone ahead and put the dots where those intercepts are. The intercept is 20 on the y-axis and 20 on the x-axis. So I'm going to go ahead and draw that budget constraint in right now. And all of the stuff that we're going to be doing with this video is going to be graphical. So it's important that I get these graphs really kind of on point. And I was off one. I thought that was looking weird. Hold on. Okay, so we're going down. There, that should be right. Let's see. Yep, that did it. Perfect. Okay, so that is his budget constraint 1. So now we're going to draw in 2 other budget constraints before we get talking about the graph. So what about if apples are $10 and oranges are $1.66, or 5/3 of a dollar? Well, if apples are $10, then I'll just go ahead and write this out up here first. So we have budget constraint 2 is that $40 is equal to 10 times the quantity of apples plus 1.66, or I'm going to write 5/3 instead, plus 5/3 times the quantity of oranges. So for the apples, if we buy no oranges, he will have $40 to spend on apples, which will mean that he will have 4 apples. So we'll go 1, 2, 3, 4. That's just putting in a 0 for O and solving for the quantity, putting in a 0 for the quantity of oranges and solving for the quantity of apples. And then if we put in a 0 for the quantity of apples, we will multiply by 3. So 40 times 3 is 120. And 120 divided by 5 is, hold on one second, so 5 goes into, I'll just do it out, screw it. So 120, 5 going in there, will go into 1 0 times, it will go in here twice, that will be 10, 20, and we'll get 24. Okay, so 24 is going to be off this graph by 2, but we'll just put it right here, and we'll call that good. Because this graph is 22 units long. I already know that just because I've worked with it a bunch. So I'm going to do my best to connect these lines that I can. That's not quite going to do it. So these should be straight lines in theory, but I can't draw that well, so we're just going to have to work with it. And we'll label this budget constraint 2. And then what about now if he only has $20 to spend and apples are $2 and oranges are $2? Well, so budget constraint 3 then, and I'm kind of running out of room, but I'll do my best, is 20 is equal to 2 times the quantity of A plus 2 times the quantity of B. And so we're going to have intercepts of 10 and 10, so we'll go, I know that this is 10 right here, and then that this is also 10 right here. And so this will be budget constraint number 3. Budget constraint 3. Okay, so now we are ready to talk about John's utility maximization problem. So on budget constraint 1, I've already kind of pre-picked these so that they're nice and pretty. But on budget constraint 1, John is as happy as he can be if he buys 10 apples and 10 oranges, if he is right here at point A. So our answer here is that he's going to buy 10 apples and he will buy 10 oranges. And here is why. The first thing is that he is on his budget constraint. So he is spending all of his money, and this is kind of, it's not saying, this isn't saying that you'll spend all your money in one day, but it's saying that you'll spend all of your money in one lifetime, really. So he's on his budget constraint, and the utility function, or his indifference curve, just barely touches his budget constraint. You can see it just barely kind of dips down here and just barely touches it. And so in math, when something just barely touches something else, we say that the indifference curve, so I'm just going to write the IC, is tangent to the budget constraint. And all that that means is that it just barely touches it. So when two curves are tangent, they share one point, and then the slope of the first curve is equal to the slope of the second curve. So the slope of the indifference curve is equal to the slope of the budget constraint. And so here's why that matters. If the slope of the indifference curve was not equal to the budget constraint, then we would get an indifference curve that had a different slope at the point where it is, well, it wouldn't be tangent, but it would have a different slope than the budget constraint. And if it has a different slope, then we know that it dips back in at some point, that it dips back underneath the budget constraint at some point. So here, the slope of the indifference curve is like this, and the slope of the budget constraint is like that. And because those two are not equal, we know that the indifference curve is going to dip down in here at some point. And so if that happens, then there's a higher indifference curve. Remember, as we go to this top right corner, this is happier. These are higher levels of utility. Then there is a different indifference curve that would touch that budget constraint at a different point, and it would have a greater utility than the one that dips underneath. So I am going to I'm going to delete all of these budget constraints that I was drawing just to clarify that. And so now we have two real big conditions, two real big things that have to be happening. First, you have to be on the budget constraint, and I'm just going to write BC. And then the second is that the indifference curve IC, has to be tangent to the budget constraint. So what this is saying in mathematical symbols is that the slope of the indifference curve has to be equal to the slope of the budget constraint. And so we already know that the slope of the budget constraint is equal to the price ratio. It's equal to the price of good X, or in this case of, you know what, we'll just do price of X over price of Y for now. So it's equal to the negative of the price ratio. And we know that we don't know this actually, but I'm going to provide a little intuition for it, and that's what we're going to have to go with. That the slope of the indifference curve is equal to the negative of the marginal utility of X over the marginal utility of Y. So here's a little explanation. if you are on the same indifference curve, you are just as happy at any 2 points. So let's pick this point and this point right here. So shifting from here to here, you gain 2 oranges and you lose, what is this, 1, 2, 3, 4, 5, 6. You lose 6 apples. So to go from this point to this point, that is, you gain 6 oranges, or no, excuse me, you gain 2 oranges and you lose 6 apples. And you are just as happy after that happens. So the marginal utility of 2 oranges has to be equal to the marginal utility of 6 apples, because you are just as happy at the end. So the marginal utility of, what is this, of 6 apples, of 6, so we'll do this. We'll do 6 times the marginal utility of apples is equal to 2 times the marginal utility of oranges. 2 times the marginal utility of O. And so this slope then is going to be the marginal utility of oranges divided by the marginal utility of apples, or the ratio of these two. So I'm going to go ahead and say, remember, it's rise over run, so we're going down 1, 2, 3, 4, 5, 6. So we have -6, and we're going right 2, which is equal to -3. And that's exactly what we got here, is that the marginal utility of oranges, the marginal utility of what's on the x-axis, so if I divide over the marginal utility of apples, and I'm just running out of room, so I'm trying to do this kind of small, we have the marginal utility of oranges divided by the marginal utility of apples is equal to 6 over 2. And then we know that we are losing 6 apples, so there really should have been a negative sign here to start. So, and that's the exact same thing that we have over here. So that's the kind of the intuition for why the slope of the indifference curve is the ratio of marginal utilities. But I'm not going to go any more in depth into that. I think that that's enough for that topic. If it's not clear, please let me know. And now we have to talk about what to me is the most important part of this entire video. So we know that the indifference curve is tangent to the budget constraint. And that means 2 things. First, that they share a point, and we can just see that right here. I'm not going to go too much more in depth into that. But also that their slopes are equal. So the price ratio, the negative P of x over P of y, has to be equal to the marginal utility of x over the marginal utility of y. And if I go back, I'm going to go back and replace these with apples and oranges. So the price of oranges, which is what's on the x-axis, negative price of O over the price of apples has to be equal to the negative marginal utility of O over the marginal utility of apples. So just rearranging a little bit, this is the same exact thing as I'm going to get rid of the negatives, and I'm going to divide this over and multiply the price up. So we're going to have the price of oranges over the marginal, actually, I'm going to flip this around. I'm going to multiply this marginal utility of apples up and divide this price of oranges over. So we're going to get the marginal utility of apples over the price of apples is equal to the marginal utility of oranges over the price of oranges. So I want to stop and talk about this equation for a little bit. So what this is saying is that the increase in happiness per dollar spent on apples has to be equal to the increase in happiness per dollar spent on oranges. So I'm going to write that out. The left side is the increase in utility for one more apple. So this is the increase in U of one apple over the price of apples, P of apples. So that is the increase in utility per dollar on apples. And this is the same thing for oranges. This is the increase in utility of $1 spent on oranges. And so what this is saying is that the amount of happiness you get per dollar for apples has to be equal to the amount of happiness you get for oranges. If it wasn't, let's say that you were happier spending money on apples than you were on oranges, and so we had the marginal utility of apples over A is greater than the marginal utility of oranges, then you should spend more money on apples. You'd buy more apples and you'd buy less oranges, and vice versa. If the marginal utility of oranges per dollar spent was greater than the marginal utility of apples per dollar spent, then you'd buy more oranges and you'd buy less apples, and you'd keep on kind of balancing this back and forth until you got to where they are exactly equal. So I hope that makes some sense intuitively. Watch it a couple times. It really does take a long time to sink in. It's a very complex idea, but that's really the best explanation that I can give for it. That's the one that makes sense in my head, and if it doesn't make sense in your head, let me know and I'll try and work something else out that might make a little more sense. So then I just want to go through, this is kind of the last theoretical thing that we have to get to, is this guy right here. Then I just want to get back to some kind of easier examples. So now what about if we're on budget constraint 2? If apples are $10 and oranges are only $1.66. Well, then we can see that the budget constraint is tangent to the indifference curve right here at point B. And so that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 oranges. So that will be 12 oranges and 2 apples. So he will buy 12 oranges and he will buy 2 apples for that exact same reason. And he could not be any happier given his resources and the prices of apples and oranges. So now what about if he only has $20 to spend and apples are $2 and oranges are $2? Well, then he will buy where the budget constraint, this third one, this red one, is tangent to and equal to his indifference curve. And that will be at this point right here at 5, 1, 2, 3, 4, 5, and up 5. And it's just, that's my poor drawing that it's kind of equal for a little while. But that really should be exactly where they touch. And so he will buy 5 apples and 5 oranges. So, in summary, when you are maximizing utility, you will always be on the budget constraint, and the indifferent curve will be tangent to the budget constraint at the point of utility maximization. And then that gives us that the kind of the bang for your buck on apples, or the bang for your buck on good X, has to be equal to the bang for your buck on good Y. So I've rambled long enough in this video. That's a lot to digest, and it really is the most important and also one of the most complicated ideas in economics. And so I'm going to stop there.